All right, so last class we talked about the difference between a statistic and a parameter. So let's look at this data set here. I could put it into my calculator, I could put these values in, and I could find out that if I put them all in my calculator and I look at, or if I just added them up and divide, I get a mean of 24.71. And that is, for that set of numbers, that is the mean. That is the population. That is the entire set of numbers. But I can, if I had a random number generator, I could pick 3 of these at random. Let's say I picked this one, and this one at random. They would have an X bar, but it would not be exactly the mean. It would be oops, sorry, I made a mistake in my math there. 25.3 repeating. Or I could have another random sample of this, this, and this, and I'd get an X bar of 23. And so out of this population, there are many different random samples I can take, and the random samples won't always come out to have the same average as the population I was drawing from. And so this whole question thing is saying how accurate an estimate can X bar be of mu? After all, if we did different random samples, we get different values of X bar. And this basic fact is called sampling variability. The value of a statistic varies in repeated sampling, right? I could send you guys out and say what percent, you could go out and run a sample. We could say go find 30 kids at random at the school, find out what percentage of the students are African American. And I would send you all out and you'd all come back with different answers because none of your samples were the same. But you're all sampling some from the same population. So the question then becomes, in order to get a sense of how much variability we should expect in sampling, what we do is we ask the question, what would happen if we did it many, many times? And if we go back to our example, right, there was this population of 7, and we were picking 3. And so that's that. And so if we were to do that in our calculator, we would have there are actually 35 different distinct individual samples I could take of 3 from that group of 7. And so what we would look at is what each one of those looks like and look at what the distribution of all of those possible samples are. So what we're doing is in real life we're going to take one sample. But we're dealing in the hypothetical. What if I took hundreds of thousands of samples and then compared all the different values together? What would that look like? And that's what we're going to be talking about today, which is what's known as a sampling distribution. And the sampling distribution of a statistic is a distribution of all values taken by the statistics and all possible samples of the same size from the same population. But once again, we're starting to a distribution, so we're going to have to describe it. And to remind you, we're describing a hypothetical distribution because no one in their right mind is actually going to do this for every single possible combination. So, this is what we're talking about. In practice, it's difficult to take all possible samples of a size n to obtain the actual sampling distribution of the statistic. At that point, why don't we just, we've asked everybody in the thing, we don't have to use a statistic because we've done a census, and we don't have to estimate with X bar. If we've asked every person, we know mu. The reason we're doing this is that there's a lot of theory behind it. And the theory will then, based on the theory, we'll be able to say with how confident we are in our guess. So here's how it works. Let's say there was some parameter. Right? We had a bucket of beads. Half of them were blue and half of them were red. And it's a massive, massive bucket. Well, it's not that massive. There's 100 blue and 100 red, so there's 200 of them. And we're going to draw a sample of 20 at random. So we have our population. In our population, we know the true parameter is 0.5. But if we draw a 20, we're not always going to get, by random chance, we're not always going to get exactly half blue and half red. Sometimes we'll get more blue than red. Sometimes we'll get more red than blue. But if we did it over and over again, what you would see, and you did a dot plot of it, you'd end up with a shape like this. And this should look vaguely familiar. And so we have three levels. You have a population. From that population, you take a sample. And I get a value for p hat. And then I do that again and 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 again. And that would be your sampling distribution. That would be the distribution of all the possible samples. And so what we're going to be talking about here is the shape of the sampling distribution and how the shape of the sampling distribution tells us how accurate our estimate is of our statistic. In real life, we wouldn't create this, but as we said, we're going to get into some theory about how this is all created. But the key is to understand the difference. So there are three levels here. There is the population distribution. I'm sorry, I just crossed that out and underlining it. There is the population distribution. That is fixed. It cannot change. The population is fixed. Then there is the distribution of the sample data. And that's this piece. This is what is the actual sample looks like. And then we're going to take each one of these p hat values and we're going to plot them. And if we do that many, many times, that gives us the sampling distribution. And we'll play with this a lot in class. Because we know there's randomness in our sample, by looking at the shape, and these should look very familiar. If we look at the sampling distribution, if we look at the center, we look at the spread, and we look at the shape, we should be able to tell how accurate our estimate is. And if these things generally follow rules, then we'll be able to tell how accurate all our estimates are. And that's where we're getting to. So our first definition is an unbiased estimator. A statistic is used to estimate a parameter as an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Well, what does that mean? Well, let's go back 2 slides again to all this data here. And let's erase everything. And let's break this down further so we can really see what's going on. So, the true proportion of the population was 0.5. So we draw a sample and we put 0.4. So I put a dot at 0.4. And then I draw another sample and I get 0.55. So I put a dot at 0.55. Then I draw another sample for p hat and I put a dot at 0.65. And we keep doing this again and again and again and again. And we eventually get the shape you see here. And so let's describe this. This is a symmetric curve, maybe even approximately normal, but the center is definitely 0.05, which was the value of the parameter. So the center of the distribution is the same as the true value of the parameter. Therefore, this is an unbiased estimator. Then, the tighter the spread on the sampling distribution, the less likely we are to be away, the smaller the standard deviation, the smaller the standard deviation of, right, it's the standard deviation of p hat, because it's the standard deviation of all the possible p hats. The smaller this number is, the better our guess is, because the less likely we are to be away from the center, and the center is the correct value. And we're getting to the point where, so when describing sampling distributions, low variability is better, because on average we're going to be closer to the center, and the center is the correct value. Now, we don't know what the center is, because in real life, we haven't taken hundreds of samples. So, but the larger our sample size, the smaller the variability will be. As the key thing is, we don't ever want to sample more than 10% of the population, which is what it's saying here in this last little bit. But the larger your sample size, the smaller the sampling, the narrower the sampling distribution will be, and the more accurate your estimate is. And this is the big one, and this is what will drive you nuts with statistics. Unfortunately, even if you use an unbiased estimate, it doesn't guarantee that you're going to get the right answer, because the sample was chosen at random, and just through random chance we can get a value that is way off. And so here is two unbiased estimates. And they use two different sample sizes. And the first one, they use a sample size 100, and it gives us this distribution. Now, it's still centered on the correct value, but if we do this and we compare it to a sample of 1,000, you can see that this one is much narrower. So what does that mean? Well, in real life, we're only going to do one sample. So in real life, let's see here, that looks like one standard deviation out there. In real life, 68% of the time we're going to wind up here, between here and here. If we take 1,000, then in real life, 68% of the time we're going to wind up between here and here, because that's one standard deviation away. And so the narrower that distribution is, the more likely we are to be closer to the center. So the larger the sample size, the more accurate our estimate will be. And here's another way to think about it. I like this bullseye analogy. I think it helps. Is that an unbiased estimate, these are unbiased estimators, A and D, because the center of them is on the bullseye. This is a biased estimate. It's not on the bullseye. This is an unbiased, this is a biased estimate because it's not on the bullseye. But these two have low variability. These two have high variability. And so what we really want is we want it to be unbiased and low variability, so all our shots end up in the bullseye. So bias means that our aim is off and we consistently miss the bullseye. And bias will come from a lot of times bias will be built into your experiment. This is why chapter 4 of the textbook was so important, is that we set things up so that they are unbiased. And then sample size is important, because the larger the sample size, the lower the variability, and the more likely we are to nail our target. Sampling distribution, sorry, they're going nuts with the PA system. Sampling distributions can take on many shapes. The same statistic can have a sampling distribution with different shapes depending on two things are going to drive the shape of the sampling distribution: the population distribution and the sample size. What's crazy is that the population distribution we don't generally know about, That's the whole reason we're taking a sample in the first place. But sample size is definitely something we can control. But we're going to consider the basic rules about these when doing inference, which is what we're moving into. Making conclusions, saying something about what we got. All right, so this is what we learned this unit. And we will experiment more with this in class next time. You can write this down. You can follow along in the book. It's the end of section 1 in the book. And everybody have a good night. See you tomorrow.